Hello everyone, my name is Mohammad Hafizul Islam and I am a PhD student at University of Central Florida. Today I will present our work, RSO New Side Channels Exploiting Read Asymmetry in MLC Phase Change Memories. This work is done under the guidance of my advisor Dr. Faniao with the collaboration of Dr. Riewitz and Dr. Ella. Information security is a major concern in today's computing space. Microarchitectural side channels are already a significant source of information leakage, with newer exploits coming up regularly. Non-volatile memories featuring phase change memory is one of the major contenders for memory subsystem in the future computing systems. Existing commercial products have been pushing for PCM memories for quite some time. To protect data in PCM-based memory, secure NVM systems focusing on data integrity protection and data remnants issue have been well studied. However, there is no prior study examining the security of PCM memory technology against timing channel attacks. Learning from prior mistakes leading to severe attacks, it is obvious that security in any computing system needs to be understood by design instead of an afterthought. In this work, we perform the first investigation of information leakage vulnerability in multi-level cell PCM. Before diving further, let us first have a brief look at PCM memory technology. PCM cells generally have wide resistance range. In a typical single-level cell PCM, the resistive range is divided into two groups storing 1-bit value. However, this resistance range can be divided into more regions. For example, in a 2-bit MLC PCM, 4 resistive states are defined to store 2 bits per PCM cell, effectively doubling the capacity of the PCM memory. While MLC PCM brings superior capacity advantages over classical memory technologies, it may complicate the read memory access technique. At the first stage of read operation in MLC PCM, the PCM cell resistance is compared against reference resistance R2. The MSB bit is determined at this stage. Depending on the comparison with R2, the cell resistance is then compared against either R1 or R3, which determines the LSB bit. Note that the MSB bit of the PCM cell can be determined right after the first stage of read operation, but the LSB bit can only be determined after the second stage. This creates a bit position dependent read latency in MLC PCM. Since read operations are in the critical path of application execution time, to improve performance of systems, there are many proposals exploiting the multiple levels of read by decoupling the MSB bit from LSB bit. Out of those proposals, interline strapping is one of the state-of-the-art technique with easy integration in existing memory controller design. In this technique, the memory controller can map one memory line entirely in the MSB bit of the PCM cell, and the next memory line is mapped entirely in the LSB bits. The MSB line can be read faster since the read can be terminated after the first stage, improving the overall system performance. This technique utilizes memory mapping to increase effective performance of MLC PCM-based memory system, leading to read asymmetry. Now that we know decoupling MSB and LSB lines to optimize system performance can bring read asymmetry, we want to ask the question if MLC PCM read technique is vulnerable to information leakage through externally observable latency difference. In order to answer this question, we develop a microbenchmark which issues a certain number of memory accesses where we can control the access ratio of MSB lines and LSB lines. In this figure, we show that by changing the LSB ratio, we can observe an almost deterministic linear increase in application execution time. Our key observation from this experiment is that differentiation in PCM access pattern can induce externally observable slow and fast executions, which can potentially lead to side channel exploitation if the access pattern is dependent on program secret. Now we present RSO, a side channel that aims to exploit the read asymmetry in MLC PCM. At a high level, RSO has 3 components. The first one is offline profiling, where the attacker obtains secret dependent memory access pattern of target application running in a local machine. The attacker can perform comprehensive profiling locally on a known victim application, which exhausts all possible secret values. In the second step, the attacker passively monitors the execution time of the victim that has an unknown program input running in a local machine. Since this is a non-intrusive attack, the attacker can manifest without any interference to the victim in the runtime. Once the execution timings from the victim are obtained, the attacker will try to perform a statistical analysis to exfiltrate the secret. Now with the RSO framework, we perform a case study on real-world application running OpenSSL AES encryption, where we try to recover the private key from a victim machine. AES encryption uses a pre-computed values from T-table for encryption or decryption, and these T-tables are stored in memory during runtime. The access pattern to this T-table is secret dependent. During the offline profiling stage of RSO, the attacker uses a local machine to create profiling dataset for AES encryption. For this, the attacker runs encryption using randomized program input and collect the LSB and MSB line ratio for each of the encryptions. He then organizes the access ratio based on the key byte value and the ciphertext byte value pair. For each value of the key byte, the attacker creates a memory pattern vector or MPV. For example, this equation shows the MPV for key byte value of U. For each value of the key byte, the MPV contains 256 access pattern ratio corresponding to all of 256 possible ciphertext value. Finally, the attacker creates profile dataset for each key byte which contains 256 MPV each. Once the profile dataset is completed, the attacker mounts runtime monitoring of AES encryption in victim machine to collect encryption latency traces. For each byte of the key value in victim machine, the attacker compiles a list of encryption timing vector or ETV which contains encryption times for each value of the ciphertext byte. This equation shows the ETV corresponding to the unknown key byte value. The attack data from the runtime monitor contains only one ETV for each of the key bytes in last round. Once the ETV is obtained from the victim system, the attacker runs correlation analysis between the ETV from the victim and the MPVs from the profiling. Hypothetically, the key value corresponding to the MPV resulting in the highest correlation with ETV may represent the unknown value of the key byte. Here on the left side, we show two example traces of MPV for key byte 0. On the right side, we show ETV obtained from the victim machine. We run correlation analysis with the ETV with the MPVs. We observe that the MPV when the key byte value is 16 results in the highest and outstanding correlation with the obtained ETV, which indeed corresponds to the secret key value of the victim machine. Similarly, we observe that we are able to recover all 16 key bytes of AES encryption in this way as shown in the bottom figure. Furthermore, we use 100 different keys in the victim machine and observe that RSO can recover all 100 keys with 98.5% accuracy. In this paper, we have more discussion about RSO, including comparison with state-of-the-art cache-based AES key recovery attack. We also discuss potential mitigations for future system. Thank you for attending this talk. If you have any question, please direct them to this email.